The word optimization means to find the best solution for a minimization or maximization problem. There are three elements which are involved in an optimization problem. First of all, we have the optimization array here, what we call X. This X is an array which is the set of variables that are unknown at the beginning of the problem. And the aim of the problem is to determine the value for all the elements of this optimization array. We will see the procedure in a while. Then we have the cost or objective function, that it's f on x. This function will depend on the variables within the optimization array. Here you have f of x, and the goal for the optimization problem will be to maximize or minimize the value of this objective function. So make this f as big as possible, or this f as small as possible. And finally, we have the third element, that are the constraints. These can be understood as the conditions that must be accomplished by all these variables in the optimization array. We have four types of constraints. First of all, the linear equality constraints, that they can be written in a matrix form, as you can see here. It's a linear combination on X. Then on the other hand, we have linear inequality constraints. They can also be written in a matrix form, okay? But here we have, as you can see here, the inequality. MATLAB only knows how to tackle problems with this kind of inequalities. So, if we work within MATLAB, you cannot use this kind of inequalities. Yeah, so you must translate these inequalities into this lower or equal than. And then on the other hand, finally, we have nonlinear equality and inequality constraints. We will not use this kind of constraints in our problems within this course, because we will have only linear constraints, as you will see. So, in order to summarize, this subject will be focused on some specific optimization problems. These kind of problems will be binary integer optimization problems. What I mean is that this X will be integer numbers, but not only integer numbers. These values in X can have value 0 or 1, okay? We don't have a huge range of values, only false or true. Then this means that variables with the optimization array are binary, false, true, integer numbers, and the constraints can be expressed in matrix form, as you can see here. This kind of optimization problems can be solved efficiently by the branch and bound algorithm. So, in order to find further information, I encourage you to find out some information about this algorithm. This is not my objective today. My goal for today's lecture is only to show you how to state, how to define an optimization problem for our aim within the course. Let's do this with a simple example. We have 6 people, can you see here? A for Anderson, B for Blackmore, then C for Campbell, D for Dickinson, E for Evans, and F for Floyd, as you can see here. Yeah, the 6 people will be assigned in a desk. So we have one person will be assigned to one desk, okay? But as you can see here in the layout of our office, we have 7 desks. So we have one desk that will be empty, okay? Because every worker will be assigned to a desk, yeah? So we have 7 desks, 6 workers, so one desk will be empty at the end of this problem, yeah? We asked for all our workers about the preferences where they want to be assigned. Obviously here we have windows, so all the people prefer to work here in front of the windows, yeah? But we have only 3 desks, so we cannot satisfy everyone. We cannot satisfy their preferences. As you can see, the preferences here are numbered, yeah? They have some quantities. Here you see that Anderson prefers to work in desk 1 only at 3%, so a very small preference. Then on desk number 2, Anderson prefers to work on desk number 2 only at 4%. And as you can see, when we reach the preferences for desk 5, 6 and 7, the preference increases with a 10, 40 and 40%. Yeah? The same goes for the other workers. As you can see, all the workers prefer to work in front of the windows. So we cannot satisfy everyone. So we need to make the difference between a worker and the others, yeah? So we will use seniority, so how long they have been working at the company, in order to make this difference, in order to weight all these preferences. As you can see, A has been working at the company for 1 year and a half, then B for along 2 years, 3 for C, D 5 years, and as you can see here, E and F are the longest periods they have been working at the company. So E and F will be taken more into consideration in order to take into account their preferences. So the preferences for Evans and Floyd will be taken into account in a greater value than the others, okay? Because here I will use the seniority as weights. As you can see here, I divide, that's divide, okay? It's an element-wise division, so that means that seniority will be divided by the sum of all the elements in seniority in order to find some kind of a percentage, okay? And as you can see here, the highest values, obviously because of that, are the values for the weights of Evans and Floyd. Then, first of all, we will define the optimization array. So these variables that must be discovered as a result of the application of the branch and bound algorithm. So first of all, we will state the meaning of all these elements and how many elements there are within this array, this optimization array X. As you can see here, we have 42 elements because we have 6 people here and we have 7 desks. So we have the possibility to have the A worker on desk number 1, 2, 3, 4, 5, 6 and 7. So if you do this for all the workers, you have 6 plus 7, 42 elements. And what is the meaning of all these individual elements? X1 is the variable within the optimization array. That means A will be assigned in desk number 1. It's only a question because, as you may know, X, all the elements in the optimization array can have false or true, and you will only know which values there are within the optimization array only at the end of the application of the algorithm as a result of the optimization problem solution. Okay, so first of all is only a question. X1 means, will A be assigned in desk number 1? We don't know if it's true, 1, or false, 0. Then on the other hand, we have X2. X2 means, will be A assigned in desk number 2? We don't know. We will know at the end of this problem. And then the same goes for 3, 4, 5, 6, and 7. So the first 7 elements of the optimization array deal with A. Then the same goes from the 8th element till the 14th element, that all of them deal with B. For example, X10 means B will be assigned in desk number 3. 1, 2, and 3. Okay? I remind you that we don't know the value for these elements within the optimization array. It's only a question for the algorithm. We will know. And as you can see here, for example, the last 7 elements here, X42 means that F Floyd will be assigned in number 7. I don't know if X42 at the end will be equal to 0. So F will not be assigned in desk number 7, or maybe this 42 at the end, within the solution of the problem, will be equal to 1, so it will mean that F will be assigned on desk number 7. I don't know, we will see. What's the objective function? The objective function deals with satisfaction. We want to satisfy our workers. I wish I could assign all the workers here in front of Windows, but I cannot do that, okay? So that's why I ask them the preferences, yeah? As you can see here, all the preferences is to work in front of the window, but I have used the seniority in order to weight these preferences. So, the objective function will be at the end a linear combination on those variables within the optimization array. And all the elements in this objective function will put into numbers the goodness of the solution. I will tell you. For example, can you see here X1? Yeah, X1 means A will be assigned in desk number 1. It's only a question. I don't know if it's true or false. I will know it at the end of the problem. Yeah, but now it's only a question. So how good is this solution? This solution satisfies the preference for A to be in 1. Can you see here? His or her preference is 3%. Can you see here? A 3%. But these 3 will be weighted by the seniority of A. Can you see here? The 0.0492. So that's why I do the product between this weight and the preference for A to be assigned in 1. Okay? Then I will add the value or the numbered value of the goodness of this solution. This solution is A in 2. What's the value? The value with which X2 contributes to the solution of the problem. Remember that I want to satisfy my workers, so I want to maximize their preferences. I want to I want to have all my workers satisfied. I wish I had, okay? So then, let's go again for what's the value, the equivalent, the numeric equivalence for A into, thanks to this element. So as you can see, it's a 4, because A wants to be in desk number 2, a 4%, yeah? But this 4, again, will be weighted by the seniority of A. Can you see here? Yeah? And the same goes for all the remaining elements of the optimization array. It's only a numerical contribution on the solution of the function to be maximized or minimized. Let's have a look at x42 and x41, as you can see here. Yeah? x41, first of all, can you see that it's the preference of the last person, remember, A, B, C, D, E, and Floyd, yeah? So that's the preference of Floyd to be in desk number 6, and the preference of Floyd to be in desk number 6 is a 40%. Can you see here? So that's the 40. And then finally, what's the weight that is associated with the seniority of Floyd? 0.2951. So that's why I apply this weight. The same weight goes for, this is Floyd in 7. So how good is this solution? This is the weight, and this is the preference of Floyd to be in 7, and it's a 50, okay? And finally, the most important thing, I want to satisfy, this is equivalent to, I told you, maximize. MATLAB only knows how to minimize. So if you want to maximize a cost function, you must put a negative. Okay, that's why I have a negative in here. Okay, it's because I want to maximize. Is how good is this satisfaction? How good is this solution? But how can I write this into how can I translate this into a MATLAB code? Here we have the preference matrix, can you see? Then I have the seniority, yeah, these are the weights, the seniority that is normalized, and then I put these weights and this preference matrix as a product, as you can see here, yeah? This is how I have translated this into an array. This is an array, this is C, and this C collects all these numbers. This is the first element of C, this is the second element of C, this is the third element of C, and as you can see, all the elements of C will be multiplied by the optimization array. Okay, so in MATLAB you must only give all the coefficients that will be multiplied by the optimization array. So at the end, F will be minus C multiplied by the optimization array. This C is a row array, yeah, while this is a column array. But MATLAB only wants to know this. These are the coefficients for every element within the optimization array. So this is for MATLAB. Okay? This, the optimization array, will be inferred by the algorithm. Okay? You must only give MATLAB this minus C. But the problem is not so simple because we have some constraints to be accomplished. The first constraint is that each person gets exactly one office, so one person cannot be assigned to more than one office, and each office has no more than one person in it. That's not the same. That means that every person is assigned to a desk. Okay, this is the first constraint, while the second constraint means that one desk will receive only one person, not more than one person. Okay, so this constraint is the opposite than this. Okay, it's the other way around. And then we have two extra constraints that either Anderson and Blackmore must work side by side, so no more than one office away. And the same goes for Dickinson and Campbell. Why? So maybe it's because Anderson and Blackmore work on the same department, and the same goes for Dickinson and Campbell. But if here I put Dickinson, Campbell must be on the right or on the left. Okay? And if I put Blackmore here, A must be here or here, but not in another position. No more than one Manhattan distance. Remember this, a Manhattan distance. That's the concept. So Manhattan distance equal to 1. That means that only one size for the Manhattan distance. So how can we tackle this problem of the constraints? First of all, each person gets exactly one office. So let's go for worker A. This x1 means A in desk 1. x2 means A in 2. And at the end, x7 means A in 7. So what am I doing here on the first equation, the first constraint? Because I know that xk belongs to this array, can be 0 or 1. With this first equation, I'm forcing that only one x between 1 and 7 can have a value of 1. So here I'm forcing to have 6 zeros and a single 1, because I know that x can have only 0 or 1. The same goes for worker B, C, D, E, and F. Let's consider F. That means F in desk 1. I'm telling that F in 1, 2, 3, 4, 5, 6, and 7, only one out of these 7 elements within the optimization array X can have a value of 1. All the 6 remaining ones will have a value of 0. I don't know which will be 1. I don't know if it will be this, 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 this. I don't know which. But I'm forcing that only one out of these 7 variables can have a value of 1. And here you have how to build these equations within the MATLAB environment. As you can see here I have done a spy of this. You remember the linear equality constraint, they have this form. Yeah, it's a linear combination on x. Can you see here? So the first equation means that I have 1x1, 1x2, 1x3, 1x4, 1x5, the same for 6 and the same for 7, and x8, 9, 10 till 42 they have a 0 coefficient, okay, because all the elements from 8 to 42, they are not present on the first equation. So that's why here I have x1, x2, 3, 4, 5, 6, and 7, and here can you see that on the first equation the remaining elements are 0 till the 42nd here element, okay, yeah. The same goes for the second equation, the third, the fourth, the fifth, and the sixth equation, because I have 6 workers, you remember? Yeah? So I have 7 ones, but these ones are shifted in every equation, because here, as you can see, here I have all the ones here, all these coefficients, I have all these coefficients shifted, yeah, 7 positions. As you can see here, the first 7 ones, the second, the third, the fourth, and the remaining ones. Yeah, all of them are shifted 7 positions, like the equations. This is the B equality. All of them equal to 1. So this means 1, 1, 1 till the end. Okay. The second kind of constraints. Each office has no more than 1 person in it. No more than 1 person. But one desk, office means desk, one desk could be empty. That's why I cannot put an equality constraint, but an inequality constraint. As you can see here, this x1 means A in desk number 1, but x8, be careful, is B in 1. This, the 15, is C in 1. Then it's D, E, and F, all of them in desk assigned to the desk number 1. Yeah, the same goes for 2, 3, 4, 5, 6, and 7. And as you can see here, I'm forcing that no more than 1 element can be equal to 1. But, for example, they all can be 0 within an equation. Why? Because you remember, I have 6 people, but I have 7 desks. So one desk, I don't know which, could be empty, okay? That's why the less or equal to 1, okay? Not equal to. If I put an equal, I'm forcing one of these elements to be 1. But I don't know, maybe all of them are 0, or maybe all of them in the second equation, or maybe in the third, I don't know. I'm sure that these desks here will not be empty, because all the people wants to work here, okay? But I'm not sure, maybe 1, 2, 3, or 4, one out of these desks will be empty, okay? This is how I translate this into a MATLAB form. This is the SPI of this A inequality 1, yeah? SPI of this matrix. So this matrix in here, as you can see, the first element, the 8th, the 15th, the first element, that's the 8th, that's the 15, can you see here? So this is the first equation with all these elements in the first row, the second equation, third, fourth, fifth, and seventh equation, because I have 7 desks. So here we have 7 equations, okay? And this here are all these ones that you can see here, because this is a SPI of B inequality 1, yeah? As you can figure out, we will have more inequality constraints, because here I have a 1, so here we will have the inequality of the second group of inequalities. Here we have an additional type of constraints, that is A and B must be no more than one office away. So let's consider all the possibilities. Here, if I put A, I don't know if this is true, but if I put A on desk number 1, B cannot be in 3, 4, 5, 6, and 7. Okay? Because if A at the end is assigned to desk number 1, B cannot be assigned in all these positions. Will be assigned here. Yeah? But we don't know if A will be assigned here. It's only a question at this moment. It's uncertain. Okay? So then, how can I say this? By means of these inequalities. Have a look. x1 means A in 1. Yeah? And then, what is x10? x10 is B in what? 8 is B in 1, 9 is B in 2, so 10 is B in C, in 3. Okay? So then this cannot be greater than 1. This avoids that both elements in the optimization array, the first and the 10th elements, both cannot have a value of 1. So both cannot be true. Okay? So if A at the end is assigned on the first desk, B for sure will not be assigned on desk number 3. And the other way around. If B here is assigned in desk number 3, so at the end, if you assigned, not you, the algorithm assigns B on desk number 3, A cannot be in 1, because both variables cannot have a value of 1, because if they were 1, this will be a 2, and 2 cannot be in here. Okay, it's smaller or equal than 1. The same goes for A in 1, B in 4, A in 1, B in 5, 6, and 7. Okay? I'm sure that some of you are thinking about the possibility to translate these 5 inequality constraints into a single inequality constraint. Okay? Because here you are forcing that all these elements, only one out of these elements can be 1, but maybe all are 0. Okay? Maybe A is not in 1 and B is not in number 3 here on the first. Okay? Because it's an inequality, not equality. So both can have 0, 1, 0, 0, 1, but not both 1. Okay? Yeah? So here I could translate these five constraints into a single one. Because, for example, if x1 is equal to 1, all the remaining elements will be equal to 0, because they cannot be, the addition cannot be greater than 1. Okay? But this kind of simplifications can only be done when the assignment is 1 to 1. Okay? 1 to 1. If, for example, I could assign a person in 2 different desks, then this is not possible. But now for this problem is the same. But I strongly recommend you to use this kind of programming. Okay? So state all the inequalities one by one. and the algorithm will take all of them into consideration. Okay, this will work under all the conditions. Okay, so here I strongly recommend you to stop the video and check that these are the 4 constraints when A is assigned on desk number 2, because B could be here or here, but not on 4, 5, 6 or 7. Okay, so 4, 5, 6 and 7. Yeah, and then I strongly recommend you to stop again the video and check all these inequalities, that they are when A is assigned on desk number 3. B cannot be in 1, can you see here the 8, yeah, and then 5, 6 and 7, 5, 6 and 7. Pay attention that I am not sure where, well, I don't know, I have no idea where will be assigned the A worker. Okay, so that's the reason of the building of all these inequality constraints. Then the same goes when A, for the possibility of A to be assigned in desk number 4, and then the same for desk number 5, 6 and 7. I recommend you to stop the video and check all these inequalities. Okay, this is the MATLAB equivalent code. As you can see here, I have inequality, second kind of inequality constraints. Yeah, I had previously the inequality 1, now I have the inequality 2. I can assure you that at the end they must be stacked all together. So for this kind of constraints, A and B no more than 1 office away, and be careful, this is more than 1 office away, because 1 office away is to be next. Okay, next, side by side. As you can see here, the distance is smaller than this. Okay, yeah, so that's why I'm considering these equations. So this at 32 inequality constraints. Yeah, all these inequalities for the previous slide and all these inequalities. At the end, they are 32 inequality constraints. But what about the final constraints that Dickinson and Campbell, they must work together side by side. So Dickinson here, Campbell on the left or on the right. Campbell here, Dickinson on the right or on the left. Okay, yeah, but this possibility is not possible. Side by side, next. Okay, so pay attention. Here I remind you about all the first inequality constraints for A and B. Remember, when A is assigned in desk number 1, B cannot be in 3, 4, 5, 6 and 7. Yeah? So now for C and D, you remember A, B, C, D, E and F, Anderson, Blackmore, yeah, all the workers. Every worker has 7 positions in the optimization array, you remember? So when you want to move from A to C, you must move 2 workers. So that's 7 positions multiplied by 2. So the same inequalities will work if you add 14 positions for A and C, and for B and D goes the same. So that's why the equations are not 1 now, but 15, because it's 1 plus 14, and not 10, but 24, because it's 10 plus 14. And here you have the third kind of inequalities, because I want C and D to be one next to the other. At the end, I must do the compilation of inequality constraints. Remember, the first inequality, only one desk can be empty. The second inequality constraints, A next to B, and the third, C next to D. Yeah, and I will solve it by means of the int linproc.m. This is the MATLAB function that solves this kind of problems. First of all, remember, this is the cost function, the objective function, yeah, this f. The second input argument, 1 to 42, means that from the element 1 till the element 42, all of them will be integers, okay? From the element 1 till the element 42. MATLAB knows how many elements there are in the optimization array because of the size of f. Then we must put the inequality constraints, can you see here? Then the equality constraints, and this other lower bounds. Yeah, that means that these elements in here from 1 to 42 means that all the elements in X will be integers, but integers can be 0, 1, 2, 3, okay? I must state that the lower bound of all the elements in X is 0. So this way I'm telling that the elements in the optimization array will be 0 as the lower bound. And then here I have the upper bound. Okay, upper bound or upper bounds. Yeah, that means that the upper bound will be 1. So all of these values will not be considered. Okay? Then, according to the seniority and the preferences, as you remember, Evans and Floyd are the workers that they have been working the longest time at the company. The seniority is bigger, is longer for this E and F. And they wish, as you can see here, to work on 5, 6, and 7. Can you see here? Yeah? And can you see that Evans, he or she, doesn't mind if he or she works on 6 or 7, because it's the same probability, okay? And as you can see here, after running the algorithm, the solution tells that Evans will be assigned on desk or to desk number 6, while Floyd will be assigned to desk number 7, because the preference of Floyd to be in number 7 is greater than in number 6, despite the seniority of Floyd is or has a smaller value of Evans, but Evans, he or she wants to work on 6 or 7 equally. Then, on the other hand, as you can see, the question is where A, B, C, and D are assigned. As you can see, the first 4 numbers are close to 0, so they don't be assigned. They don't want to be assigned in 1, 2, 3, or 4. But because A and B must be together, and C and D, they must be together, they will be assigned on the last row, not in front of the windows, but on the back of the room. One possibility would be to assign B and A, for example, in the front row, but they don't have enough seniority. And the same goes for D and C. They could be assigned here, but as you can see, they don't have enough seniority, the same that happens with A and B.